Hello all, welcome back to AK Apt Logics. Today in this class we are going to discuss about how to write the design code for NOT gate using the switch level model. In the previous class we have discussed about gate level model, data flow model and also behavioral model. We have seen nearly 10 number of styles. Okay, not 10, close to 10, right? So today in this class we are going to discuss about switch level model. So switch level model is quite different compared to previous models. If you know digital electronics and have an basic C knowledge, then you can able to write all the styles which we have discussed previously. But for writing the switch level modeling design code, you need to have knowledge on the internal details of the design, which means we need to have a knowledge on transistors. Okay, internally the transistors used in the NOT gate will be different. Some of them may use CMOS technology, some of them may use TTL, some of them may use ECL technology. Like this, there are so many technologies at DTL, diode transistor logic. Like this, we are having so many number of different number of technologies will be used in the internal details of the design. The most and important design which we are going to see in our BTech or um, which we are going to have a low power consumption technology, CMOS technology. Okay, the CMOS is basically combination of both NMOS and PMOS transistor. If you are not going to have that knowledge on CMOS and CMOS technology, then I recommend you guys to don't watch this video. Why? Because you feel you feel like you're not going to understand anything. Okay, I'm also can't able to say that particular technology in detail right now. Okay, so I'm going to give you simple overview. Okay, CMOS is CMOS technology basically have is of two types. One is it is having pull up network, pull up network, and it is also having pull down network. I'm going to give you some basic knowledge, okay, but it is not sufficient for you. Okay, pull down network. Okay, what is meant by pull up and what is meant by pull down? Why these names got pull up and pull down means the pull up networks consist of PMOSs. It is consisting of PMOS transistors. It will be consisting of PMOS transistors, whereas pull down network will consist of NMOS transistors. Pull down will consist of NMOS transistors. Okay, we will combine both of them and we will apply input to the both of the networks. We are going to apply inputs to both of the networks and we are going to give two types of voltages. One is high voltage, that is VDD, which is called as VDD, to the pull up network, and we are going to give low voltage, which is called as VSS, to the pull down network. From where we are going to take output is from the common point of joining the both pull up and pull down network. We are going to take the output from this point. We are going to take the output. Okay, so this is the basic understanding that you need to understand. Okay, so why this pull up is called as pull up network and why this pull down will call as pull down network, let me discuss you very easily. Okay, so for example, we are going to use PMOS and NMOS, right? we are going to use PMOS and NMOS, both PMOS plus NMOS, so that this technology name is called as CMOS, which is complementary metal oxide semiconductor. Okay, PMOS means P channel MOSFET and NMOS means N channel MOSFET. We are going to use both the PMOS and NMOS, so that we are going to call it as CMOS, which is complementary metal oxide semiconductor. The PMOS will be seen like this when we are going to use in the CMOS technology. It is not the actual representation, but it is used because to have an ease of drawing. The PMOS will be seen like this. Okay, this is PMOS and this is NMOS. This is NMOS. The only difference you can able to observe here is the bubble. Okay, this is the gate terminal. This is the drain terminal. This is the source terminal. Similarly, we are going to have gate, drain, and then source. We are going to apply the input to the gate terminal. We are going to apply the input to the gate terminal of PMOS, and we are going to apply input to the gate terminal of NMOS. Okay, for drain and source we are going to give this VDD and VSS supplies. Okay, and we are going to apply inputs to the gate terminal. At the joint of both PMOS and NMOS, we are going to take the output of our design. Till this, all of you clear, right? So when will this particular PMOS will get to on, and when this particular NMOS will get to on? Basically, our whole operation will be between switching operation only. Okay, on and off. There will be only two states of operation, that is on and off, and there will be some of the leakage currents, all this stuff that in detail we are not going to see. Okay, we are going to have only on and off. Okay, whether this transistor can be on or this transistor can be in the state of off. Similarly, the NMOS transistor as well, it can be on or it can be in the state of off. When it is going to on or when it is going to off, I am going to tell you now. These points you need to remember. Okay, I'm going to give you a little bit discussion, that's it. When you are going to apply input, when we are going to apply input, either it may be the high voltage or it may be the low voltage. High voltage in the sense 5 volts, low voltage in the sense 0 volts. Generally there will be some of the margins. Okay, from 0 to 2 volts, if you are going to apply any input, then it will be treated as logic 0 or the low voltage. From 3 to 5, if you are going to apply any voltage, then it will be treated as logic 1 or high voltage, and you will get output correspondingly according to that. And if you are going to apply input in between 2 volts to 3 volts range, then it will be invalid, or you can't able to say how the design is going to behave. Okay, these are the margins. Some of the margins will be there for every technology. There will be different margins. Okay, next, if you are going to apply input as 0 for the PMOS, if you are going to apply input as 0 for the PMOS, then it will turn on. Okay, how you need to remember this? There is a bubble, right? There is a bubble, right? We are going to apply 0. It is going to turn on. Okay, it will be the opposite in the NMOS. NMOS, for NMOS, if you are going to give the input as 0, then it is going to turn off, not on. It is going to turn off. Okay, if you are going to give the input as 1 to the NMOS, sorry, to the PMOS, then it is going to turn off. It is going to turn off. When you're going to give the input as 1 to the NMOS, then it is going to turn on. Okay, this is the basic points you need to remember. Okay, and I have told you, right, why this is called as pull up and why this is called as pull down. We are going to discuss when we have completed the example of NOT gate. Okay, see, now I am going to make the NOT gate. Okay, now I am going to make the NOT gate. How many inputs does the NOT gate have? One input. I am letting it be y a, and I am letting it be, I am letting the output be y. Okay, and we are going to have two supplies. Those are VDD and VSS. VDD and VSS. These things will be also treated as input. These are also the input voltages, right? To give the supply to the transistors. Next, now what I have told, in the pull-up network we are going to have the PMOS, right? In the pull-down network we are going to have the NMOS, right? And the point you need to remember is, here we are going to have only one input, right? That is A. So that in the pull-up network you are going to have only one PMOS. Similarly, in the pull-down network you are going to have only one NMOS. Always the PMOS count and NMOS count will be equal to each other in the CMOS technology. Okay. Now, if you are going to treat this as drain terminal of PMOS and then source terminals of PMOS, and this will be the drain terminal of PMOS and this will be the source terminal of NMOS. What I have told you, for the pull-up network we are going to apply the VDD. VDD in the sense high voltage. VDD we are going to give it over here. VDD in bracket, for example, it will be the 5 volts. 5 volts power supply to the source of NMOS. We are going to apply the VSS, right, which is of 0 volts actually, or let us treat it as ground, which is equal to 0 volts. Now, for both the pull up and pull down network we are going to apply the input, right, as per our discussion, right? For the gate terminal of PMOS and also for the gate terminal of NMOS we are going to apply the input, so that I am going to join both of them and giving the input, which is A in our case, and we are going to join the source and drain which are left in the PMOS and NMOS, and we are going to take the output from them, which is Y, right? So now we have made a design. Now I am telling that this is a NOT gate. This is a NOT gate. Why? Because I know it. And the basic gate in CMOS is NOT gate. A basic gate in CMOS is basic gate that we can able to design in the CMOS, or the first gate, or the minimum number of transistors to a gate that is having is NOT gate. You can remember anyhow. Okay, I know that it is a NOT gate. Okay, so but before NOT gate we are having another gate, right? That is buffer, right? But most of the people think that this has a buffer. No, it's not the buffer. It's the NOT gate. We are going to have a complement output. Complement, right? Complementary metal oxide semiconductor, in which complementary means we are going to get complementing outputs. It means it's the NOT gate. If you are going to have a doubt, let us first apply 0 to this particular design. When you are going to apply the 0 to this, then which of the transistor will turn on? Any one of them will turn on, whether it may be the pull-up network or it may be the pull-down network. Any one of them will turn on. What it is? For 0, as per our above discussion, PMOS will turn on, right? PMOS will turn on in the sense it will turn on like this. It means it will just acting as a switch, right? For 0, NMOS will be turn off, right? It means it is going to have open switch. Open switch in the sense there is no any connection. Now what will be our output? There is a closed switch, right? This is the closed switch. This is the open switch, right? This is the open switch. This is the closed switch. Why? Because we have applied the 0 voltage, so that PMOS is turning on and NMOS is turning off. And NMOS is acting as a open switch and PMOS is acting as a closed switch. So what is the output? We are getting VDD, that is 5 volts applied to the output, right? Like this. In this path we are going to get VDD, which is 5 volts applied to the output. It means we are getting the high output, so that we are going to get logic 1, or we are going to get output as 5 volts. When we applied logic 0 or 0 volts, we got the output as 5 volts, right? Whenever there is a logic 0 as input to the design, we are going to get the output as 1. This is the first case. Second case, the other input that is possible is logic 1 or 5 volts. Logic 1, which is called as 5 volts, and you are going to apply 5 volts to this particular input pin A or the logic 1. Then what happens is NMOS will be turned on, right? NMOS will be turned on, whereas PMOS will be turned off. For logic 1, NMOS will be turned on and PMOS will be turned off. And you can see there is a path from VSS to output Y. Like this we are going to have path, right? Means then Y will be equal to how much? Y will be equal to 0 or the 0 volts, right? Whenever we applied the logical 1 or 5 volts to the input, we are going to see the output as 0 volts. Now which operation this circuit behave like? Not operation, right? So that I am told that this is a NOT gate. Okay, now the point why PMOS transistors network will be called as pull-up network, and why NMOS transistors network called as pull-down network. Means whenever you are going to apply the first case, that is 0 volts, PMOS is turned on, right? PMOS is turned on and NMOS is turned off. When the PMOS is turned on, output is getting pulled up from 0 to 5 volts, right? Output is becoming 1 whenever we are going to apply the 0 volts to the PMOS, and when the PMOS is turned on, output is getting 5 volts or logic higher, right? It means it is pulling up the voltage from low voltage to high voltage. It is pulling up the voltage from low voltage to high voltage at the output. Okay, so that we call PMOS network in the above as pull-up network. Why? Because it is pulling up the output to VDD or the high voltage. Why we are going to call NMOS network or the pull-down network as pull-down network? Means when you are going to apply the logic 1, which is high voltage, then NMOS will be turned on, whereas the PMOS will be turned off. At that point of time, output is getting pulled down to output voltage that is 0 volts from a high voltage, so that it is getting pulled down, right? The output is getting pulled down, so that we are going to tell the network as pull down network. Okay, I think I have given you a basic knowledge about the CMOS. Okay, I hope you understood how to design circuit for the NOT gate in the CMOS technology. When we are going to discuss about the AND gate, I am going to discuss at that point of time how we are going to design all this point. Okay, so just let me pause the video and just draw the circuit again for you. Just a second. See guys, this is the NOT gate in the CMOS technology, right? You can take any other technology. There will be pseudo NMOS, uh, there will be by CMOS. Like this, we are going to have so many number of technologies. For all those technologies, you can write the code in gate level model. Okay, oh, sorry, switch level model. I'm saying that gate level model. Sorry, switch level model. Okay. Now TB is same, right? Our TB is same. For any design, TB will be same. Whether you are not going to change the module name or the input names, then TB is same for any design code. Okay, so let me implement the code in the switch level. Okay, this is the circuit. Now we got the circuit. How does the NOT gate looks in the CMOS technology? There are so many technologies, but I am going to discuss about CMOS technology because most of the people discuss about the CMOS technology only. There are by CMOS, only NMOS, only PMOS, TTL, ECL. Like this, there are so many technologies. Okay, now this design code will be changed. Okay, just a second. Yeah, so everything is same. Module, module name, input, output, everything is same. And we need to remove the always block which is belonging to the behavioral model, and we have a end module. Okay, now at this point of time, how we need to do the how we need to write the code for the switch level model. First we need to observe what are the inputs and output, what are the outputs in our circuit. So if we are going to observe what are the inputs and what are our outputs, A will be our input, right? VDD will be our input and VSS will be also will be our input, and Y will be our output. This will be our output. Remaining all three will be inputs, right? But you need to specify this input in only in the port list itself. You need to specify only A in the port list. Why? Because these two inputs are applied to give the biasing of the transistors. So I'm going to, it is a very typical concept which is in the EDC. Okay, I'm not going to discuss because I even don't know about those biasing or all those stuff. Okay, so you need to give this input in the post list only, and also you need to give output this output in the port list. Then how we are going to specify this VDD and VSS? I'm going to discuss that. Okay, so the port list also same for the switch level model. The port list also same. Okay, let me change it to switch level model. Okay, port list is also same, right? But there are additional two inputs, right? But there are additional two inputs which are VDD and VSS. How we are going to specify them in the code? So for that we are going to have a keyword that is supply1 and supply0. Supply1 in the sense supply high voltage, or the supply logic 1, for which we need to supply logic 1 or high voltage. For the VDD or VSS, we are going to supply logical 1 to the VDD, right? So I am going to give the VDD semicolon, and the next supply 0 VSS. Okay, I'm going to apply 0 to the VSS. Okay, now we have given all the inputs. Okay, main input and output will be specified in the port list, and the power supplies will be specified in the code itself. Okay, you shouldn't specify them in the port list. If you are going to specify them, then there will be some difficulty. Okay, the TB will be changed, right? The TB will be changed, so that I'm not going to specify them in the port list. I have given the supplies and also I have defined the port list. Now what we are going to do? Now what we are going to do is, in gate level model we are having the primitives, right? Those are nothing but the keywords of gates. Not gate, for not gate we are going to have not, and for AND gate we are going to have AND. Till now we haven't discussed, but we are going to discuss those as well, those also in the future. Okay, don't worry. Like this we are going to have primitives. In the switch level model also we are going to have primitives for the transistors. Okay, for PMOS there is a primitive. Okay, for the NMOS there is a primitive. For PMOS primitive it will be called as PMOS. For NMOS primitive it will be called as NMOS. First let us take PMOS, which is a primitive for the PMOS. Now we need to give the instance name P0. Instance name is nothing but just simply we are going to give the instance name is nothing but just we are going to simply give this PMOS as P0. We are going to give name for this PMOS. That's it. And we are going to open the parenthesis and close it and semicolon. Now in this parenthesis what we are going to specify, what we need to specify. Okay, okay, so for that I'm going to tell you in very detailed manner. See, how many terminals does this particular PMOS contain? How many terminals that uh, whether this particular PMOS contain? Let me mark it. This is one input, right? This is terminals, not inputs and outputs. Just leave it. Terminals. This is one terminal. This is another terminal, and this is another terminal. Total there are three terminals. So that we need to mention three parameters in this parenthesis. Okay, there are total three terminals, so that we need to give three parameters, and for those three terminals what are the values connected, what are the values that are connected. For gate terminal A is connected, and for the drain terminal VDD is connected, and for the source terminal Y is connected. Okay, Y, this is the Y, right? Y is connected. We have also known that values which are connected to the three terminals of PMOS, those are A and then VDD and then Y. These are the three values that are connected to the PMOS in the pull-up network. Okay, so in which order you need to specify them? This is the most important thing. In which order you need to specify them in the braces? Let me discuss that. Yes, sorry, I have mistaken. Okay, see, I have told you, right? See, this is the drain, I told you, right? No, this is not the drain. This is the source, and this is the source for the NMOS, and this is the source for the PMOS, and we are going to connect both of the drains, okay. Let me draw another, or I am going to specify over here, just a second. So this will be the gate, this will be the gate terminal, and this will be the gate terminal for both the PMOS and NMOS, and For which terminal we are going to give the supply, that terminal will be treated as source. This is the source terminal, and this terminal is the source terminal. Okay, and this is the drain terminal. This is the drain terminal. Both the drain terminals are connected, and from both the drain terminals we are going to take the output Y. Okay, don't get confused. Okay, I hope you have an clarity now. See, in the parenthesis, which value we need to give first for the PMOS? We have already found out, right? A, VDD and comma Y. These are the three values we need to give in the parenthesis. In which order we need to give? First we need to give the drain. Drain in the sense this, right? We need to give the source, drain, source, followed by gate. Okay. For drain, what is connected? Output Y is connected, right? From drain only we are going to take the output. Okay. Yeah. And for source, what is connected? Supply VDD is connected. And for gate, what is connected? Input A is connected. So we need to specify them like this. Okay. First we need to specify the what is connected to the drain. Second, we need to specify the what is connected to the let me write this for you over here. This is the format. Okay, this is the comments. Two forward flashes are used, two comment, and let me write the format for you. First you need to give the drain value, then source, then followed by gate value. Now I am going to write for the NMOS. See, I am going to assume NMOS instance as N0. It means I am giving a name for this NMOS. I am going to give a name for this NMOS. That is N0. Okay. Opening the parenthesis and then closing it. In the NMOS also we need to specify three values. Why? Because NMOS is containing three terminals. Okay. In the same order we need to specify. That is first drain, then source, then gate. For the drain terminal which is connected, same Y is connected, right? See, Y is connected. For the drain terminal, Y is connected. And for the source terminal, what is connected? VSS is connected. So you need to give VSS. And for the gate terminal, A is connected. So I need to give the A. I'm going to write format for the NMOS as well. NMOS N0 drain source and then gate. Okay, so this is what our code. Anything left unconnected? No, right? There is no anything left unconnected. We have total two transistors, those are PMOS and NMOSs. We have taken two primitives or the keyboards and connected them accordingly. And we have total four connections. Three are the inputs, one is the main input and one is the main output. Other two are the supply inputs we have taken, and we have taken two instances, those are PMOS and NMOS, for two transistors. So let me adjust the screen for you. Okay, now this is the code of our NOT gate in the switch level model. Okay, switch level model in the CMOS. Okay, this is a CMOS code. There are so many number of styles. We are having only PMOS, only NMOS, all the styles. There are different numbers of styles in the switch level model. Okay, to write the code for those switch level models, you must know the technology. Here I have explained you the CMOS technology first. See, I have given you a briefing about CMOS technology first, and then I moved on to designing of inverter or the NOT gate using the CMOS technology, and then I have told you how to write the code in switch level model. If you want to learn the uh, if you want to write the code for the not getting the by CMOS model, then you need to know that particular technology. You need to have a basic knowledge about that particular technology. If you want to write the not get uh, not get your switch level code for the NMOS technology, then you need to write the code for the then you need to learn the only NMOS technology. If you want to write code in only PMOS technology, then you need to learn the code. Then you need to learn about the only PMOS technology. Okay, this is how we are going to do. So I hope you understand about the code, how I have written the code, and I think you got some basic knowledge about the CMOS technology. Okay? I am going to discuss for every design which is possible to me to tell you. Okay, in the switch level model. Okay, for the larger designs, I mostly skip this particular switch level model because it is having so much of difficulty. Possibly, I'm going to discuss. Uh, okay, so I mostly discuss for the gates, and I will try to discuss for the half header, full header, those things as well, and also yeah. If not in CMOS, I will try to discuss in any other models. For example, for multiplexer, if you are going to take the multiplexer, for multiplexer, it is very easy to write the code in fast transistor logic. Okay, there are the problem here is not the writing code is very easy, but learning that particular technologies is the most difficult part. Okay, so that we doesn't proceed with the switch level model. Okay, I'm going to stop at some particular point. Okay, at some particular point, I'm going to stop discussing about the switch level model. But it is better to know. Okay, it's not complete necessary. Mostly, we are going to design our designs using the RTL or behavioral model or gate level model. That's it. We are not going to use this particular switch level model mostly. Okay, so but it's better to know. So let me run the code. I haven't run it yet. Sorry. Otherwise, you might read something. Uh, you might read that I have written something which is not possible. So you can be able to see the output, right? Output is, yeah, when the input is 0, we are getting the output as 1, and when the input is 1, we are going to get the output as 0. So in the console also, we are going to see the output. When the input is 0, we are going to get the output as 1, and when the input is 1, we are going to get the output as 0. So this is all about the lecture. It's quite long. Why? Because it's most important, right? Knowing is most important than learning. If you know, that's enough. Learning will take some more time, right? If you know, just that's enough. Okay. Anyway, you are going to learn it. Okay, when time comes. Okay. Thank you.